Drift, diffusion, and recombination can be demonstrated and measured in 3 experiments that we shall show. Our experiments use a fundamental physics configuration consisting of a source, a transmitting medium, and a detector. The transmitting medium is the N-type germanium rod of 5 ohm centimeter resistivity, having a high concentration of majority electrons compared to minority holes. These electrons carry current in a uniform electric field E produced by a battery. The source of minority holes is a flash of light whose photons have enough energy to eject electrons from the valence bonds and make hole electron pairs. Few enough of these carriers are generated so that they carry negligible current compared to the majority carriers, and therefore they do not significantly disturb the uniform electric field E. In this undisturbed field, the holes drift towards a detecting electrical contact. With this source medium detector configuration, we can measure the transit time, T, and the distance, W, and thus determine drift velocity, W divided by T equals d sub d. Before our experiments, drift velocity was not measured directly, but instead inferred from conductivity and Hall effect. Furthermore, conductivity and Hall effect are concerned chiefly with majority carriers and give little or no information about minority carriers. In contrast, our experiments focus attention on the motion of a pulse of minority holes. We shall show first that the disturbance produced by the light does move along the rod in the direction expected for a positive charge with constant drift velocity as required by the mobility equation, namely drift velocity d sub d equals electric field E times a constant mu called the mobility, which depends on temperature.
The basic quantities involved in the measurement of mobility are voltage, length, and time. We measure voltage with a voltmeter, length with a millimeter scale, and time with a cathode ray oscilloscope. This box contains our light source. The light comes in bursts, about 3 times a second, from a xenon flash tube. We can look at the intensity of this light as a function of time by allowing some of it to fall on this photocell and displaying the photocell response on the oscilloscope. The horizontal scale is 1 microsecond per division, so our light pulse is less than 1 microsecond long. When we do the experiment, the light is focused on the germanium bar by our optical system, which we mount over the germanium bar. The germanium bar is 2 centimeters long, and the bar is about 1 millimeter in cross-section. It is smooth and mirror-like, having been polished and etched with acid, and specially treated to minimize surface effects. The batteries that produce the uniform electric field are here. They are connected through this switch and potentiometer to these large area, low resistance contacts at either ends of the bar. To determine the electric field in the bar, we will later measure the voltage between these 2 phosphor-bronze wires. These wires are pointed and make small area contacts to the surface of the bar.
The detailed nature of the 4 electrical connections to the bar is important. In particular, the right-hand point contact is also used as the detector of minority holes. This point contact to the germanium rod has a rectifying voltage current characteristic. This characteristic can be studied by setting up a 60-cycle alternating current circuit through the point. The point is connected to the vertical input of the oscilloscope so as to show positive voltage upwards. The resistor is connected to the horizontal scope input to show current from the point into the germanium as a deflection to the right. The voltage current characteristic on the scope shows that for negative voltages, the current is barely perceptible. This negative polarity, corresponding to difficult current flow, is called the reverse direction or reverse polarity. Positive voltage on the point produces relatively large currents and is called the easy flow or forward direction. This rectifying voltage current characteristic comes from the detector point and not from the low resistance end contact. We can show this by changing this connection from the point to the other end contact. The voltage current characteristic you now see is quite different from the previous one. You see then that the rectifying characteristic must come from the point and not from the end contacts or from resistance along the bar. To use the point as a detector, we provide a reverse bias and use a resistor to show current changes, and we provide a connection to the vertical scope input here. If a pulse of minority holes passes under the point, the holes are attracted by the negative applied voltage. Some of these holes are collected, and their current flows momentarily in this circuit, producing a positive voltage signal, delta V, and upwards deflection on the oscilloscope.
In the detector circuit, which Bill just described, we use this 22.5 volt battery to reverse bias the right-hand point. The lead from the negative terminal is connected through a resistor to this brass strip, which holds the detector point. The resistor is chosen for best signal-to-noise ratio. This probe will be connected to the vertical input of the oscilloscope to monitor our detector current, and this is the ground. Now we're ready to focus the light on our bar using the right half of this binocular microscope for our lens system. Here it is. The zero of our distance scale is set at this point. To measure the time it takes the disturbance generated by the light to move down the bar under the influence of the electric field to the detector, the start of each oscilloscope sweep is synchronized to the light flash. To do this, we use the output of the photocell to trigger the horizontal sweep of the oscilloscope. When I cover the photocell, the sweep stops. Now we're ready to plug in our detector. Look at this. When Bill and I first saw such a pulse, we really knew we were detecting holes moving down the germanium bar. To show you that this pulse is actually what we thought it was, let me point out the following. First, when I prevent the light from reaching the bar, the pulse disappears. Second, there's a long time delay between the light flash and the arrival of the disturbance at our detector. Our horizontal scale is 10 microseconds per centimeter. So the pulse is arriving 30 microseconds after the light flash, a drift time much too long for normal electrical disturbances. Also, when I move the microscope stage, changing the distance between the source and the detector, the delay time changes. Third, the disturbance which drifts down the bar moves like a positive charge, as we believe it should. The electrical field is now directed from the source toward the detector. And if we remove the field, there is no pulse. And finally, if we reverse the field, there is still no pulse. So only when the electrical field is directed from the source to the detector do we see a delayed pulse. Since we believe we are producing electron-hole pairs with our light source, the detector must be collecting positive holes which drift down the bar under the influence of the electrical field. According to the mobility equation, the velocity should decrease when the electric field is decreased. When we decrease the field with a potentiometer, the delay time increases as expected and decreases when we raise the field again. Now we are ready to measure the electric field in the bar. I'll connect the voltmeter to the two phosphor bronze points. The voltage between the points is 9.70 volts. The points were set at 1.25 centimeters apart. So the field in the bar is 9.70 divided by 1.25, which is 7.76 volts per centimeter. With this fixed field, we can show that the delay time is directly proportional to the distance from the source to the detector. To show this, I will connect this constant speed motor to the microscope stage. Now, as the detector moves away from the light spot, we can also watch the movement of the pulse. The two movements are synchronized, indicating that time and distance are directly proportional. Thus, the drift velocity of the holes is constant. To measure the drift velocity, we moved the detector by equal increments of distance and took still pictures of the pulses. Here we have plotted delay time as a function of the distance from the source to the detector. Dividing this distance by the time, we get a pulse drift velocity of 1.29 times 10 to the fourth centimeters per second. Dividing this velocity by the electric field of 7.76 volts per centimeter gives us a mobility of 1.66 times 10 to the third, or about 1,700 centimeters squared per volt second. This value applies at 31 degrees centigrade, which is the temperature of the bar with the present electrical power input.
Our first experiment has shown that the minority hole pulse moves like a positive charge with constant drift velocity. Our second experiment is concerned with the shape of the pulse. You have noticed that as the delay time increases, the pulse becomes shorter and fatter. To understand this, we consider hole concentration as a function of distance. When the holes start out bunched together in a narrow pulse, there are big concentration gradients, and diffusion spreads them out rapidly as they drift down the bar. Now for our case, consider the width of the pulse at half maximum hole concentration. This width, W sub p, we obtain only indirectly by measuring the time interval that this width, W sub p, takes to pass under the detector at speed v sub d, so that the time interval t sub p times v sub d equals the width w sub t. Actually, the pulse changes shape a little as it passes under the detector, but our pulses move fast enough to permit neglecting this effect. Now for our case of diffusion in a uniform electric field. The width w sub p depends only on the transit time t and the whole diffusion constant with dimensions of centimeters squared per second. The only dimensionally correct relationship between w sub p, the transit time t, and the diffusion constant d is wp squared is proportional to d times t. We used diffusion theory to calculate the proportionality constant. To compare this theory with experiment, we express w sub p in terms of t sub p and v sub d and obtain this equation. In order to use this equation to test diffusion theory and to measure d, Dick Haynes must first show that the whole concentration at the detector is proportional to the scope deflection delta V.
The deflection is proportional to the concentration of holes under the detector point. Many other experiments show that such linearity is a property of a reversed biased detector rectifier. You will understand more about the reasons for this when you study PN junctions. However, we can make a linearity check here. This pulse is now averaging 4 units high. The slight variations in height are due to slight variations in light flash intensity. Let me trace over one of these pulses, which is exactly 4 units high. Now I'll cut the light intensity in half by covering one of these two holes through which the light passes. The resulting pulse height has fallen to 2 units, but I can raise it to 4 units again by doubling the gain of the oscilloscope. Now you can see that the whole pulses that are 4 units high coincide at all points with the pulse for full light intensity. This coincidence of the pulses shows that the oscilloscope deflection is proportional to the whole concentration under the detector. To get the diffusion constant, we measure the width for the pulse as it moves out from the sweep origin in time t. For various delay times t, we measure the time duration, t sub p, of the pulse here, between points where the pulse height is half its peak value, corresponding to the half concentration value of Bell's formula. On this chart, we have plotted the values of t sub p square as a function of the transit time t. As you see, the data points fall close to a straight line in keeping with Bell's equation. The slope of the straight line is 2.86 microseconds. Solving Bell's equation for the diffusion constant d, we get d is equal to the drift velocity, v sub d squared, divided by 1107, multiplied by the slope of the line. The result is a diffusion constant of 42.9 centimeters squared per second for minority carrier holes in our bar at 31 degrees centigrade.
The diffusion constant and the mobility of the holes have values governed by random thermal motion. The importance of thermal motion is expressed by the Einstein relation, which requires that the ratio d over mu be equal to kT over q, in which kT is random thermal energy and q the electron charge. This ratio has the dimensions of volts and is called thermal voltage. I regard it as the most important single number in semiconductor electronics. The convenient value to remember for it, near room temperature, is 1/40th volt.
This value of the diffusion constant, divided by our mobility value of 1.66 times 10 to the third centimeters squared per volt second, is equal to 0.0258 volts, which is consistent with theory.
We now come to recombination. When I described the spreading caused by diffusion, I represented these two areas as equal, corresponding to a constant number of holes. Actually, as they drift down the rod, holes recombine with electrons, and the total number of holes is represented by this area. The simplest model for recombination predicts that this area decays exponentially with increasing transit time with a time constant, tau, called the lifetime.
Using our pictures again, we have plotted pulse areas as a function of delay time on semi-logarithmic coordinates. The vertical axis is the pulse area, which you remember is proportional to the number of holes which succeed in reaching the detector. The horizontal axis is the transit time of the holes. The data points scatter, but as you can see, they can be approximated by a straight line. From this line, we find that the number of carriers decreases by 1 over e in time tau. Tau is equal to 51 microseconds, and this is therefore the lifetime of the holes in our bar.
The measurement of lifetime completes our three experiments showing that minority holes drift, diffuse, and disappear by recombination. Similar experiments can be carried out with p-type germanium. The results give values for mobility, diffusion constant, and lifetime for minority electrons.
You have seen the hole pulse in n-type germanium move in the direction of the electric field. Had we used p-type germanium, we would have found the electron pulse to move in the opposite direction. Now, if we had used intrinsic material, where the concentrations of electrons and holes are equal, we would have found that a pulse of electron-hole pairs did not move at all in an electric field, but merely spread out by diffusion, with a diffusion constant intermediate between that of electrons and holes. This behavior is not explained by Bell's simple analysis. You remember he concentrated attention completely on the minority holes and neglected completely the reduction of the electric field in the pulse. He was able to do this, however, only because in our experiment the minority carriers were truly a small minority. When the concentrations of electrons and holes becomes at all comparable, you must consider the effect of the disturbance of the electric field on carriers of both signs.